Welcome to Control 4 Driver Development Essentials. My name is Peter Casenza. The purpose of this video is to expand upon the content outlined in the previous training module, using tables to structure data correctly. In that video, we discussed how Lua tables can be used to manage our driver data in a manner that makes sending information to a device efficient and repeatable. This video will address the second part of the driver communication architecture, parsing data that is sent from the device to the Control 4 system architecture. Before we begin examining how the device data is parsed, it will be useful to look at the data types that we should expect from a device. Those include ASCII and hexadecimal formats. ASCII is a character encoding format that is based upon the alphabet. It encodes 128 specific characters into 7-bit binary integers. The characters include the numbers 0 through 9, the letters A through Z, some punctuation symbols, control codes, and a blank space. The other commonly used encoding format is hexadecimal. Hexadecimal, also known as hex, uses 16 symbols to represent values 0 through 9 and upper and lower cases of A, B, C, D, E, and F to represent values 10 through 15. Your device's protocol documentation will provide you with the data format that the device uses to communicate. Once you have established the type of data, or string type, that your device uses for communication, you're in a position to have your driver listen for those string types and trap them when they become available. Let's look at some of the functions delivered in the DriverWorks SDK that help accomplish this. In previous training modules, we discussed the role of several DriverWorks APIs that are used to handle data that comes from the device. These APIs have the ability to receive the data string based on the control method used by the device. For example, we have the API calls received from network and received from serial. Received from network traps data strings sent from devices that are controlled through TCP/IP connection, and received from serial traps strings from serially controlled devices. These APIs do not work alone. They are assisted by a series of what we refer to as helper functions that can perform numerous actions on the data string once it is trapped by the API. Some of these helper functions include parse packet, get message, and handle message. These functions demonstrate examples of some of the Lua data parsing commands that are available to you for use in parsing the data that is received from your device. Now that we've discussed the process behind trapping and parsing device data, let's take a look at a driver in the driver editor environment and see the APIs and helper functions being used. Once again, we'll use the receiver driver that was reviewed in our previous training module. Using the script screen found in the codes and commands area of driver editor, we can find an example of the Receive from Serial API in use. You'll notice that the API receives an ID binding and a data string parameter. The ID binding represents the binding value of the control connection that the data string will be passed through, and the str data parameter represents the actual data string. If you look at this instance of Receive from Serial, you'll notice the use of gReceiveBuffer. gReceiveBuffer has the ability to store data strings that come from our device. This buffer acts as a queue of sorts. Data strings enter this queue and are allowed to accumulate. Below gReceiveBuffer, you can see several helper functions referenced. The first is getMessage. GetMessage pulls data strings from gReceiveBuffer. It pulls them in the order in which they entered the buffer. It it will pull the strings on a first in, first out basis. So, the first data string to enter the buffer will be pulled from getMessage, followed by the second, and so on. Once they are pulled from the buffer, they are deleted. Below getMessage, you'll see another helper function called handleMessage. HandleMessage parses the data delivered in the string that was just pulled out of gReceive buffer in getMessage and modifies it into a format that is consumable by the Control4 system. GetMessage and HandleMessage work in a loop that constantly examine the contents of gReceive buffer, pull out data strings, and parse them. Now that we have a parsed data string that the Control4 system can understand, a notify function can be delivered that sends the parsed packet to the proxy. The proxy will then, in turn, update any user interfaces with the device information. Let's take a minute and review the steps that we have just discussed. We reviewed our protocol documentation to determine what data formatting scheme is used by our device. We saw how a DriverWorks API was used to receive the data strings sent by the device through an appropriate control ID binding. Next, we looked at the use of a buffer that stores the data strings that come in through the API. Then we saw how two helper functions pull the strings from the buffer and parse the strings into a format that can be used throughout the Control4 system. Finally, we saw how a notify command can use the parsed data strings to update the Control4 environment with the information delivered by the device. Let's take each of these steps and examine them in detail. To begin, let's make the assumption that the device data has been received through the Receive from Network or the Receive from Serial API. The API places the data in its original format into a global variable which serves as a buffer in our parsing operations. The data enters the buffer and is allowed to accumulate there. It then calls the parse packet function. Next, a function named getMessage is called from within parse packet. The purpose of getMessage is to parse the contents of the buffer to find specific messages embedded in the device data. As a driver developer, you will need to configure the getMessage function to look for messages in the buffer while taking into consideration your device's protocol specification. We will address configuring getMessage and other functions in the next video using Lua functions to parse data and create command strings. Once a message is identified in the buffer and parsed, it is immediately removed and the next data string is examined by getMessage. Data strings are parsed in the order that they arrive in the buffer. The first data string to enter the buffer will be parsed first and then removed, followed by the second, and so on. For example, consider a receiver that uses ASCII for its communication purposes. Simply knowing that the device uses ASCII is only one part of successfully configuring getMessage. The way the ASCII messages are formatted must also be considered. Here is a sample of ASCII messages from our receiver that currently reside in the buffer. Using our protocol documentation, we know that messages from this receiver are separated by a carriage return, or /R. So we need to configure getMessage to look for messages delimited by carriage returns. If getMessage is configured correctly, it will be able to parse out MV space 25. Again, using our device protocol documentation, we can ascertain that MV represents the volume for the main zone, and the 25 value indicated the new volume level. The logic can be seen in this code block, specifically this line of code. You'll note that a Lua function called string.match is used in this code example. We will explain how string.match can parse through data in our next training module. Now, we have successfully parsed an individual message from a string of numerous messages within the buffer. This represents the first half of parsing data in your driver. The second half of the parsing methodology involves taking that individual message from the device and translating it into a format that the Control4 proxy can understand. To accomplish this, we'll use a function named handleMessage. Before we get into the details surrounding the handleMessage function, it will be worthwhile reviewing some of the concepts that we discussed in our previous video, Structuring Data Correctly. Particularly, the concept of using tables to manage not just values, but also to store functions. In the methodology shown here, we employ several tables which are populated with protocol data that will be used in translating device messages into notifications. If we open the receiver proxy template in Driver Editor, we can view these global tables. The tables in which we are most interested for this example are the dev_message table and the notify table. The dev_message table holds all of the device messages that you want to handle in your driver. In most cases, devices send messages with two components, a name and a value. For example, our receiver has the ability to send a message when the volume has changed. Its message type is ASCII, and the message, after being parsed out by getMessage, looks like this: VL54. The VL portion of the message needs to reside within the dev_message table. The notified table is used to list all of the notifications that are supported by the Control4 receiver proxy. If you start your driver using a Control4 template, the majority of this table is already populated for you. In keeping with our volume change example, we'll need to create a function that can handle the device message by sending the appropriate notification to the proxy. In this example, we created the function dev_message.vl. This function uses a parameter which represents the volume value that comes from the device message. When the function is called, it fires a notification to the proxy. The proxy notification is a predefined notification recognized by the receiver proxy called volume level changed. Its parameters are the new volume level and the output that is indicated in the device message. This is just one example of handling a simple message from a device and sending a notification to the proxy. As a driver developer, you will need to evaluate all of the possible messages that might come from your device and decide which of those you would like to support. After that, you'll need to populate the dev_message table with those messages and create a function for each that will send a notification. Let's look at another ASCII volume changing example that is somewhat more complex. Consider a receiver protocol that communicates its volume levels across a range of values that consist of -80 through +20. The Control4 receiver proxy only recognizes volume values using a range of 0% through 100%. In order to successfully parse the volume change string from the receiver, we will need to modify it so the proxy can understand it. For example, let's say that the getMessage function pulls a data string from the buffer that looks like this. We know that VL represents a volume level change, and that a command resides in our dev_message table. We need to modify the value it contains to match an acceptable value for the receiver proxy. So far, we've used ASCII data types to review the data parsing methodology. Now, let's take a look at a hexadecimal example. As mentioned earlier, hexadecimal uses 16 symbols to represent values 0 through 9, and upper and lower cases of A, B, C, D, E, and F to represent values 10 through 15. And like ASCII, you'll rely heavily on your device's protocol documentation to understand the manner in which the device communicates using the hexadecimal format. Before we take a look at how the hex data is actually parsed, let's look at an example of how a data string is structured. It is important to understand that each device protocol will be different. What follows is an example that illustrates the key elements that are typically included in hex data messages. In this example, you can see how each piece of the message serves a specific purpose. The first piece of the string is called the header. From our protocol documentation, we know that the header consists of the hex value FE with a length of 1 byte. This is useful information for us as we can configure the getMessage function to look for the header value in the buffer. When it successfully locates a valid header, it will then examine the data immediately following it for information. Immediately following the header is a piece of data that indicates the byte length of the actual device message. Its size is 1 byte. This information is good to know because it tells us how many bytes we'll need to look for in the next piece of code, which is the data envelope. Our protocol documentation tells us the next data piece in the string is the actual data envelope. The contents of this piece of data can vary depending on the message being sent. All of the possible messages are defined in hexadecimal in our protocol document. We do, however, know that the length constraints on this part of the string range from 3 bytes up to 250 bytes. Our device also includes a checksum piece in its hexadecimal string. It immediately follows the data envelope. The purpose of the checksum piece is to provide a summation of all bytes starting with and including the header byte all the way to the end of the data envelope. Its data length is also 1 byte. The use of a checksum value is helpful as it can be used to validate the data that is contained in the string. Since the checksum value represents the correct value of bytes in a correctly formed package, validating the package byte value against the checksum value can identify strings that are not properly formed. Finally, our device's data string has a tail which indicates the end of a string. Its value is FF, and its length is 1 byte. This is helpful as finding this value within the data indicates the end of one message. Now we have an overview of what our device's hexadecimal string looks like. Let's go back and examine the data envelope piece of the string further. This piece of data contains the actual device message, and it has its own formatting rules. The format for the data envelope looks like this. The first piece of data represents an actual command, and its values range from 0 to FC. It is 1 byte in length. Next is a subcommand that can be passed. It too is 1 byte in length, and like the command data, it can range from 0 to FC. Finally, the last piece of data includes the actual message data itself. Its valid values are 0 to FD, and its data length can range from 0 to 247 bytes. Now, let's look at an example hexadecimal string from our receiver and see how all of the pieces are put together to send a message indicating that the receiver's volume has increased to a level of 85%. Our string looks like this. We know that the FE is the header for the string. The 03 data reflects the total length of the upcoming data envelope. This would be 3 bytes in our example. Next, we have the actual data envelope. It starts with 06. this data represents a volume increase. Next, we can see that the 00, or subcommand, is not used in our example. This is followed by 55. 55 is the hexadecimal value for 85. 07 data is our checksum value, and that is followed by FF, which is the tail for the entire data string. It is important to keep in mind that the functions we outlined in our previous ASCII example are still applicable with hexadecimal data. We will receive the message through either receive from serial or receive from network. The message data strings will be placed into the buffer. The parse packet routine is called, and getMessage examines the data for data elements that are header and tail values. GetMessage then pulls the complete data string from the buffer and calls handleMessage. HandleMessage then parses the data envelope for the message contents. If the message contents have been associated with a notification in the dev_message table, a notification is sent to the proxy which reflects the content of the message. Hopefully, this training module has provided you with an overview on how inbound data is handled by a device driver. The data flow and functions used are the same regardless of the data type. Once you understand the data parsing workflow, you'll be in a good position to watch the next video in our training series, using Lua functions to parse data and create command strings. In the upcoming video, we will examine the individual Lua functions that are used to pull the data strings from the buffer, break them down into usable pieces of schema, and associate them with defined notifications to support two-way device communication. In addition to this, we will also look at examples of using these functions to send data to a device.